This lecture is to discuss soil energy flows, and the main outcome that we see from changes in soil energy are changes in the temperature of the soil. So as we'll see, there are a number of processes which affect the temperature in soil, and temperature in soil then goes on to affect a number of different things that are important for soil functioning or soil management. So we're going to look at inputs and outputs of energy into the soil system and have a look at the concept of soil energy balance. And then we'll have a look at some of the processes for which soil temperature is important and how we might be able to manage that. And these outcomes, learning outcomes, are on LMS, and we'll have a look at those again at the end. So all of the energy ultimately that the Earth receives comes from the sun. And so we need to understand a little bit about solar insolation, or the incoming solar energy, so that we can understand energy inputs into soils. So just remember that the Earth is on a fixed angle, basically, and rotating around at the axis that goes between the poles, which means that different parts of the Earth receive different intensities of radiation. So we get the most intense radiation, as we know, at the equator, and the least intense at the poles. If we plot it, we can see that effect graphically. So insolation on the horizontal axis against the latitude, either north or south. This graph, for some reason, is upside down. A bit weird compared with the diagram at the left anyway, but you get the idea. And so not only are there latitudinal effects, so less at the poles, more in the equator, but there are also seasonal effects as well. Okay, so we need to consider those, at least conceptually, as well. And one of the other things that affects the amount of solar energy arriving at the Earth's surface is topography. And the maps shown here show some information on that. And what we can see is that the slope direction and steepness of slope, the maps for those look somewhat similar to the solar radiation maps. And particularly in winter, the slope direction maps will look very much like the solar radiation received maps, and that's because, in this case, in the northern hemisphere, this is in California, south-facing slopes are going to receive far more solar radiation than north-facing slopes. In Australia, it's the other way around. Our north-facing slopes receive the most energy, and that effect is more pronounced at higher latitudes than it is at lower latitudes. So you might want to think about some of the reasons for that. So we need to consider both where we are on the Earth and where we are in relation to the local topography as well. Okay. The surface energy balance, so right at the very interface between the soil and the air, the energy balance looks something like this. We've got the net incoming solar radiation, which is always given the symbol J, and the subscript N meaning net. Okay, so that incoming radiation must be equal to the heat that's transferred within the soil, the heat transferred out of the soil by convection and conduction, so just kind of radiative or loss within convecting fluids and so forth. And there's also what we call the latent or evaporative heat flux leaving the soil, which is a function of the evaporation rate, E, times the latent heat of the evaporating water. Okay, and what that means basically is that it takes solar energy to evaporate water, and so the change in phase from water as a liquid to water vapor is effectively an energy loss from the soil system. And diagrammatically it looks a little bit like this. So the net radiation is equal to the transfer of heat within the soil plus whatever's lost by 2 different mechanisms. The other way of thinking about this is the incoming radiation can go one of 3 ways. It can heat up the soil, it can be lost as a normal or sensible heat flux, that is just loss of heat as radiative loss or convective loss, or can be lost as evaporating water. The amount to which heat is transferred within the soil or lost from the surface depends on things like texture and water content of soil, and to some extent porosity. So we can see, let's look at things like thermal conductivity. So how fast energy can be transferred through the soil. Okay, and it's different for sand and clay, and much different for a peaty soil. And what seems to be controlling it there is the porosity being much higher for peat. So the solids are able to transmit energy in soils much more easily than the pore space, which contains water or fluids. Okay. Now, thermal conductivity is better for a wet soil. So we've got 3 levels of soil moisture for each type of material here. A little bit higher for the peat than for the mineral soils, but that just reflects a much higher water retention capacity of the peat. What we can see is that water and that thermal conductivity also increases with wetter soil. So basically, water-filled pores conduct heat better than air-filled pores, and we would expect that. Okay, air-filled pores are likely to be quite an insulator. Heat capacity, how much the soil can store in terms of heat, also depends on a little bit on water content, not so much on texture, you'll notice, and quite a bit on the type of material. So the difference between mineral soils and organic soils is larger than the basically absent difference between the 2 mineral soils. And the other thing that we're looking at in this table is damping depth, the depth beyond which there's no real change in day-night temperature. And that's, again, similar for the 2 mineral soils, and a bit shallower because of the insulating capacity of the more porous peat. Okay, so what do we see here? Thermal conductivity of a sand is greater than clay, and thermal conductivity of a wet soil is greater than a dry soil. So a little summary line at the bottom there, and this is from Daniel Hillel's Introduction to Soil Physics textbook. Now, the amount of net solar radiation is not trivial. So remember, a couple of slides ago we looked at the energy balance in soils, and we just put in on the left-hand side the net incoming solar radiation. Well, let's have a look at, in a couple of slides' time, what affects that. All right, so the net incoming solar radiation is a function of, well, basically an additive function of the direct solar radiation, so shortwave radiation in the visible or ultraviolet, and indirect solar radiation, so basically the sun heating up the atmosphere or clouds and then radiating energy down towards the Earth's surface. It's what we call the indirect solar radiation. If we add up those 2 and multiply it by a certain factor, and this is important, it's 1 minus the albedo. And albedo, some of you may know this, is the reflectivity coefficient of our surface, right? So how much of the incoming radiation is reflected back. So, and that depends on the nature of the surface. For example, ice and snow is very reflective, and some types of clouds are very reflective, so they bounce the radiation back. But some surfaces, for example, darker or wetter surfaces, actually absorb a lot of the incoming radiation and have a low albedo, right? So that factor is really important. And then there is the incoming long wave radiation in the infrared or longer wavelengths, and also we notice there's a minus sign here for the radiation emission from the soil itself, because soil which is heated up by absorption of shorter wavelength radiation can emit longer wavelength radiation as it cools down, and that's something that needs to be considered as well. So the amount net incoming solar radiation, JN, hitting the soil is kind of slightly more complex than an additive sum of the incoming radiation, because we need to consider albedo. And if we include or combine those two equations, the net solar radiation equation with our energy balance equation, let's just flip back up a couple of slides to have a look. So remember, our energy balance had to look like this. The energy must be the sum of the three different ways that it goes: soil transfer, sensible heat flux, and evaporative heat flux. Okay. So if that's true, the incoming radiation minus all of those things must be zero. In other words, the energy coming in balances the energy going out of the system or remaining in the soil. Okay. So the S minus A minus LE, that's energy remaining in the soil or being lost from the soil system. And the other parts, the J parts plus the albedo, represent the energy coming in. So energy coming in minus the energy going out is zero. Let's have a look at this albedo thing. So as I mentioned before, things like snow and some types of high altitude cloud have very high albedos. They might reflect upwards of 80% sometimes of the incoming solar radiation. Soil materials tend to be down at the bottom here. So let's zoom in on those a little bit. And what we see is that we have different albedo or reflectivity of different types of material. One of the main things that we see is that soils and vegetated areas tend to have lower albedo than dry, bare soils. So wet soil is less reflective than dry soil. Sand is more reflective than, I beg your pardon. So yeah, dry sand is more reflective than dry soil. So there's a bit of a textural effect there, and so on. Okay, so basically, in order for solar radiation to be absorbed, we want a low albedo. So we're looking at either a wet soil or a vegetated system to maximize that. In contrast, dry soils or unvegetated systems reflect more of the incoming solar radiation. Now, the absorption of solar radiation by the soil, this is where it starts to make a difference, actually creates soil temperature differences. So that energy absorption by the soil is expressed as a temperature increase. Now, the temperature doesn't increase evenly all the way down the soil profile. As you would expect, it varies from day to night, and also varies from shallow to deep. And so let's just unpack this diagram a little bit and highlight the curves that we want to have a look at. So at 0 meters, right at the soil surface, during the day, the soil heats up the most, right? As you'd expect, it takes the immediate incident solar radiation right on the surface, but also cools very quickly. So energy is able to be lost from the surface of the soil very easily. It's not insulated by any overlying material, right? And so it cools down overnight by the largest amount as well. Okay, and about here is where the sunrise is. About well, maybe somewhere before that, and about here would be where sunset is over here. Okay, scrub that. Let's draw the lines. Okay, so sunset probably about here, and sunrise about here. All right. 12 hours apart, idealized. Now, what's really interesting about this is that the situation is not the same. There are two things that occur as we go deeper in the soil profile. Okay, one of them is that the soil doesn't heat up so much. So if we look, for example, at the 20 centimeter or 0.2 meter curve, the brown one that I'm tracking along here, we're getting about half the temperature increase that we are with the soil right at the surface, maybe a bit less than half. But also notice that it heats up later, so it lags behind. That's the second point I made there, and it lags behind because the overlying soil, the 0 to 20 centimeter soil above that, it takes time for energy to be conducted through that. All right, so there's thermal conductivity through a partly insulating material. So it doesn't heat up so much, not as much energy reaches that depth, and it reaches it later because of the non-instantaneous nature of heat transfer in soils. And so at some depth, these fluctuations will be effectively zero, and that was what we looked at before. Okay, so as we go deeper in the soil, the temperature fluctuations become less pronounced, and the maxima and minima are later compared with right in the surface soil. So this is related to thermal insulation. If you can explain that sort of thing, that's quite a useful thing to be able to do, because it covers a few of the concepts that we need to know about energy transfer in soils. And of course, we also need to know that the fluctuations are there because the energy is coming from solar radiation, which of course varies from night to day and back again. Okay, so soil temperature has an effect on a whole bunch of things. One of them being evapotranspiration. So the warmer the soil, the more evapotranspiration we get. All right. So even for the same amount of solar radiation, we see that effect. So let's just take one vertical line, say at 2 by 10 to the 7 joules per square meter per day, and we've got soil at 13 degrees and 21 degrees and 29 degrees. And so the evapotranspiration increases as the soil temperature increases, even though the amount of solar radiation is the same. All right, we can pick another value of solar radiation as well. This is J subscript N on our horizontal axis, and we can see that effect. All right, so obviously, the more solar radiation that a soil receives, the more evapotranspiration there is, but it's also controlled by soil temperature. So solar radiation and soil temperature and the loss of soil water by evapotranspiration, that's evaporation plus the transpiration of plants. So some of the temperature effect is on the physiology of plants themselves. We call them those linked or coupled parameters and processes. All right. So it's really hard to change solar radiation without changing soil temperature and soil water as well, and so on. Temperature also has quite a large effect on the decomposition of soil organic matter. That's what we call soil respiration, reflecting the activity of soil microorganisms in decomposing soil organic matter. All right, so what we see here is that as temperature increases, microbial activity increases, but only up to a point, because at some critical point, it's going to get too hot for microorganisms to function, and therefore microbial activity decreases again. So there's a sweet spot, if you like, an ideal temperature for microbial activity measured by, in this case, they're calling the maximal catalytic rate, let's say the rate of respiration. The other thing that we notice is that there are different curves depending on where in the world we come from. So the microbial community from a cold climate has its optimum temperature lower than the microbial community from a warm, say a tropical climate, because in each case the organisms are adapted and selected for their particular environment. Okay? So microbes from a cold climate are more sensitive to heat than microbes from a warm climate, but conversely, microbes from a cold climate are less sensitive to cold than microbes as fungi and bacteria and archaea and protozoa and whatnot from a warm climate. And if you look at the trends, and this is, I guess, a little bit worrying, that soil respiration seems to be increasing the further we move down our timeline as well. And that is most likely due to the phenomenon of global warming that we see happening all over the world, and particularly since 2000. It'd be interesting to see how the data look. Right? So there's an overall increase in respiration rate due to global warming. Okay. Now there are another couple of processes that we'll deal with. These are not the only ones, of course, but here's a look at the rate of alteration or weathering of rock materials. So relative weathering rate relative to the rate at 15 degrees. You've got to choose a number. That's what these authors chose. And showing that as you increase temperature, so the relative rate is 1, of course, at 15. As you increase the temperature, then the relative weathering rate also increases. Now, these data are for typical types of silicate minerals, feldspars, and chain silicates like augite. But the same principles apply. Most chemical reactions increase their rate with increasing temperature, and weathering is no exception to that. In managed systems like agriculture, soil temperature is really important for phenomena like seed germination. So the germination of seeds is sensitive to temperature, and of course the seeds are sitting in the soil, so their temperature will reflect the temperature of the soil. So here's a couple of effects. So this graph from this paper here, looking at the effects of both soil water content and soil temperature. We've got 3 bars at each temperature, basically. One for a dry soil, one for 9% water, one for 18% water. You'd have to look at the original article to know whether that represents anywhere near field capacity or saturation or what it represents. But nevertheless, we see an effect. So the main effect is for germination rate to increase as temperature increases, but there's a different behavior depending on soil water content. So for a moist soil, which is not restricting the uptake of water by the germinating seed, we see that there's a fairly consistent increase up to about a maximum temperature of 25 to 30. For a dry soil, we actually see a decrease after a maximum temperature of 25. So these numbers on the bottom here are just basically night, day, minimum and maximum temperatures. And for the dry soil, too high a temperature obviously is having some sort of effect, possibly by making the seed too dry to germinate completely. All right. So if soil temperature is so important, if it affects so many things, how can we manage it? Well, we can do a couple of things, and there are a couple of categories that we can put our management strategies into. One is by modifying the net radiation hitting the soil surface. Okay, so we can apply things that change the albedo or create shading, for example, mulches and crop residues. Or we can change the amount of soil surface that's exposed. That means we change the distances required for thermal conduction, maybe increase or decrease depending on which technique that we use. Aspect of site, I won't show you an example for that, but for example, it's quite common to have vineyards, even in somewhere like Western Australia, on north-facing slopes. So that's partly to give the vines more light, but also would affect soil temperature as well. Okay, cultivation. So conventional tillage can affect soil temperature. So in conventional tillage, we're mixing the soil. We're putting a lot more of the soil surface in contact with the atmosphere, and that would be expected to give rise to a different soil temperature because of the way that heat is gained or lost from that system, compared with a minimum tillage soil where there may be very little disturbance of the soil surface. Let's have a look at that and some data. So tillage affecting soil. So here's a one diurnal cycle from midnight through to midnight, and we're looking at profiles of soil temperature. Okay, and we've got different treatments here, and I'm just going to focus on a couple of them. Okay, these three here: the air temperature, DTD, which is our disc tillage, and NTSTD, which is this one here, no tillage with standing residues, dryland wheat in both cases. So something similar to agriculture in Western Australia. So the air temperature, as we expect, fluctuates through a fairly typical daylight cycle. Overnight, it gets down to about 17, 18 degrees, hitting 34, 35 degrees during the day and then dropping back down. Soil temperatures quite a bit higher. So in the no-till soil, we're getting soil temperatures in scenario A of, in the no-till, up around 55 degrees and about 50 degrees for the disc tillage, so warmer soils in the no-till. That's not always the case though. Scenario B, again, you'd have to look at the original paper for what the scenarios are. The soil is again hotter than the air, but the order is reversed. Okay, sorry, this is irrigated. A and B are irrigated and not irrigated. Silly me. All right, so under the irrigated system, actually the no-till system is a little bit cooler, and overall both soils are cooler than their dryland counterparts, showing the effect of soil water as well. Okay, so the style of cultivation makes a difference, but probably not as much as soil water content, and therefore irrigation does in this case. Okay, the other thing that we can do to modify soil temperatures is to apply mulch. Now, of course, mulch is also applied for weed control sometimes, but mulching also changes soil temperature. And so we can have a look at that. So there's organic mulches like straw or other things, bark sometimes used in other situations, or plastic mulches, which are quite common in horticulture. Let's have a look at the effects of some of those with some data. And this data set is about plastic mulching, looking at soil temperature under different types of, or basically different colors and maybe textures of mulching plastic, right? And the data and the statistical analysis which followed showed that mulch color has a lot less effect than you'd expect. So there's no significant difference even between white and black mulch plastic, but there is a difference between the mulch, many of them, and the bare soil, which is what you would expect. The mulched soils in this case are warmer. So whereas an insulating mulch, like an organic, might cause lower soil temperatures, often the plastic mulches are used to retain energy in the soil and raise the soil temperature. Okay, raised beds. So with raised beds, we're decreasing thermal conduction differences so that we can have energy entering soil from the side as well as from the top, basically. We're also loosening soil and so forth. And these are raised beds in some of the Western Australian agricultural area. Of course, they're also used to deal with things like waterlogging and aeration, but they also would affect soil temperature. So raised beds and mulch, there's a data set here. This is the effects of raised bed and mulching on the right-hand side. But let's just have a look. So compared with the flat soil, the hand-hoed soil, the raised beds and the ridged soil has a slightly higher soil temperature, which is consistent across the growing season. And in this case, the organic mulch serves to lower the soil temperature. So that's a bit different from the plastic mulches that we saw, okay, compared with bare ground. So we can do quite a lot of things to manage the inputs and outputs of energy from soils and thereby modify soil temperature. So just to summarize, if we're going to think about soil energy flows, we need to consider what happens with sunlight, okay? So, and what affects the net solar radiation which is arriving on the soil surface. Solar energy is modified by albedo, where we are on the Earth and where we are on a slope. So latitude and angle to the sun, and shading, which we can modify, of course, with mulches and so forth. Energy is always conserved, so the amount of energy going in matches the energy going out of the soil system or being retained in. We've seen a bunch of ways in which we can modify soil temperature, and soil temperature itself is very important because it affects a whole lot of other soil processes, for example, soil respiration, soil water, and so on. Okay, so in particular, soil radiation and soil temperature and soil water are strongly linked or coupled processes. So soil water represents a soil property in itself, but the evaporation of soil water is also part of our energy balance and so on. Okay, and we can leave it there. Thanks for watching.